Okay, so welcome to Math Stat 345. This is lecture 17. And so what I want to do today, will let me advance, is talk a little bit about linearity of expectation, variances and covariances, the power of linearity of expectation. This is one of my favorite techniques in all of mathematics. It's just amazing how many things can be solved using linearity of expectation. You sometimes can't get a control of the fluctuations, but then you need to understand the variances, which is a lot harder, but it's a really good start. We'll talk about some specific distributions, the Bernoulli and the binomial. We've talked about uniform already and Deviation a little bit. The further we go in the semester, the more different distributions we're going to meet. And the more distributions you meet, the more likely you are to be able to that can do a reasonable job of modeling whatever it is you care about. That doesn't mean a perfect job, but a job that's good enough. I will briefly review covariances, or not covariances, convolutions. And then the general item for today is the algebra. I did not bring the Rubik's Cube as I brought the Rubik's Cube before, but so much of mathematics comes down to, can you find a good way to view the quantities that you have to do so that you can actually see how to simplify the algebra and get a nice answer at the end of the day. If you're just running numerical simulations, it doesn't really matter if you can do this, the computer's just going to plug away. But if you can get a closed form answer, which has some parameter dependence, and then you can say, well, if I change this parameter by 5%, how does this change the result? That's absolutely wonderful. One of my former students was actually just recently interviewed talking about climate models. He is not talking about, does climate change happen? Does climate change not happen? He's talking about how sensitive are some of these models to values of parameters. And what are the dangers when you have models that are extremely sensitive to parameters? Another good example is some of the models that describe what will happen with COVID and other pandemics. What happens if you change some of these parameters ever so slightly? All right, so we talked a little bit about some of these earlier, but just for definiteness, let's just put them all back on the board. So the first is linearity of expectation. What does that mean? It means if I've got a couple of variables, x1 to xn, or it doesn't say anything about independence, it just says random variables x1 through xn. So you always want to be watching what are the conditions. There are no restrictions. That's what makes this so powerful, is that we don't need independence. For the other stuff, we need independence. So if we have a bunch of random variables, then the expected value of a linear combination, so this is one of the few times where it's actually useful to have taken linear algebra. I'm not actually adding vectors, I'm just talking about the more general idea of a linear combination. And so we look at a1 times g1 of x1 all the way up to plus an times gn, the last one. In the special case, when all the g's are the identity function, it would just be a1 x1 plus a2 x2, and so on and so on and so on. And what this is saying is the expected value of the sum is the sum of the expected values. Now, the expected value of g1 of x1 is not g1 of the expected value. You can't just switch the expected value into g, but it says that if I want to calculate the expected value of the sum, it's the sum of the expected values. In the special case when g of x is just identically c, then the expected value, of course, is just going to be c. That means there's no variation going on. All right, the next one is what does it mean? Mean and variance. So if x is a random variable with mean ux and variance sigma x squared, that means u is going to be the integral from minus infinity to infinity of x times the density function of x dx. And then the variance, you can look at it as the expected value of x squared minus the expected value of x squared, or the expected value of x minus mu squared, where mu is the expected value of x. So the real definition of variance, we normally use the expected value of x minus mu squared. But by doing a little bit of algebra and expanding out, it's the same as the expected value of x squared minus the square of the expected value. What kind of number is the variance? So what possible numbers could the variance be? So give me a possible variance in a distribution. Imagine you have scores on an exam. The average is a 50. We'll say the class maximum is a 60. Can somebody give me a possible value for the variance, how the scores might be spread out, or the standard deviation? 10. Reasonable. Could the variance be 2? Yeah, if the variance is 2, that means the scores are very tight. Could the variance be -3? No, the variance can't be negative. When you look at the definition of the expected value of x minus mu squared, it's clear that that can't be negative. When you look at the expected value of x squared minus the square of the expected value of x, it's not at all clear from that definition that variance has to be non-negative. So again, different expressions are useful. From a computational perspective, if you can compute moments easily, it's actually not too bad to use the expected value of x squared minus the square of the expected value of x. And what theorem, I'm sorry, lemma 9.5.2, it's not big enough to be called a theorem. What it basically says is, what if I tweak my variable a little bit? What if I multiply all the values of x by a, and then I add b to everything? How does that change the mean? How does that change the variance? And the answer is, straightforward algebra, and it's pretty much what you would expect. If I'm multiplying all the values of x by a, I increase the mean initially by a factor of a. Think of it as converting everybody's height from feet to yards. So what's the conversion factor between feet and yards? 3. So your height will be decreased in the numerical value by a factor of 3 if we start measuring your height in yards, right? I would be surprised if anybody here even made it up to 3 yards, but I would be shocked if anybody here was not at least 3 feet. So depending on what unit we use, we just get a different number. And then the b is to say, well, look, if I add b to everything, then the mean should go up by b. So it's extremely intuitive. For the variance, notice the variance doesn't depend on b at all. Well, again, that makes sense because we're looking at how things depend, how things are fluctuating about the mean. If I look at the definition of the expected value of x minus mu squared, if I add b to x and I add b to the mean, then it cancels. Notice how much easier it is to see in that case than it is when you look at the difference in the two expected values. And then the other thing is, it's just how things change. If I multiply every value by a, when I'm looking at the squares, I'm going to multiply things by squares. And what's nice is, notice that a squared is never going to be negative. So even if I rescale and I say, let's let y equal -x, I'm not going to get a negative value for the variance because I always square the a's. So again, always nice to have consistency checks. And then I guess I actually was kind of like, no, I do not call this a theorem. It's still a lemma. The variance of x is the expected value of x squared minus the expected value of x squared. This is just an algebraic calculation. And so strongly urge you to make sure you know how to do that. Okay. So now, this is one where we now finally have something that mentions independence. So here we have independent variables. Then the expected value of a product is the product of the expected values. And then a particularly important case is the expected value of x minus its mean times the expected value of y minus its mean is 0. Well, if the expected value of a product is the product of the expected values, I'm now changing x, so I'm subtracting off its mean. What is the expected value of x minus its means?
Zero.
0. Excellent, right? Thank you, God. Right? It's just going to be 0. Now, we do have to prove, and this we have to be careful, prove if x and y are independent. So let's say x tilde, which will be x minus mu x, and y tilde, which would be y minus mu y. So if we can prove that given x and y are independent, then these simple translations are independent, then we can just immediately use the expected value of a product as the product of the expected values and deduce. Okay, so how would we prove this? Well, we go back, we use that definition, and the key thing is you always want to ask, if I'm given a condition probability or any subject, what does that condition give me? So if I tell you that the random variables are independent, It means the probability density function factors as the product of the densities. That's the real difference. Do you expect that this theorem would hold true if x and y are not independent? All right, so give me a good example. Say x equals x and y equals x. So clearly not independent. The expected value of x squared would then be the expected value of x times the expected value of x. Do you think this is always the case? Can you give me a random variable x where the expected value of x squared is not the product of the expected values? What would be a good choice to take? If you're ever not sure, what's the simplest distribution you can think of? Uniform. Where do you want the uniform centered? 0. So take x to be uniform on -1, 1, then the expected value of x equals 0. The expected value of x squared is greater than 0. So you always want to be able to generate some quick counterexamples. And this is basically saying, if I have a symmetric random variable, if I have a random variable that has mean 0, then its square is always going to have to be 0. The only way that can happen is if all of your mass is concentrated at 0. So it's extremely unlikely that that would be the case. All right, so let's look at the proof. So the key idea is the density function of f of xy, xy factors as the density function of x times the density function of y as independent. So from our quick calculation above, we know we have to use independence somewhere in the argument. And the best place to use it is to think about what does it mean to calculate the joint density function. Because explicitly, it's just, yeah, so the expected value of xy would be the integral minus infinity to infinity, minus infinity to infinity, xy, fxy, xy, dx, dy. And now I can split this. X goes from minus infinity to infinity, x times the density of x dx, integral y goes from minus infinity to infinity of y, density function of y dy. But this integral is just the expected value of x, and this integral is just the expected value of y. And so we now have the expected value of a product of independent random variables. So expected value product of independent random variables is equal to the product of the expected values. And that's going to be extremely useful for a lot of analysis. So I like to try to remember the big results by phrases like this. The log of a product is the sum of the logs. The derivative of a sum is the sum of the derivatives. Sometimes you're careful and you would say the derivative of a finite sum is the finite sum of the derivatives. Here we have to make sure we keep the word independent. Okay, so the next one is a little bit more involved. So the mean and the variances of sums of random variables. So imagine we have x1 through xn of random variables. So what word is missing that you might like to see? Independent. So this is basically saying this is just a sum of random variables. You would expect then that the result is not going to be as good. The more restrictions you put on, the more you can eliminate bad examples from happening. So we're just having a sum of random variables. So we're going to let x, capital X, be the sum of x1 through xn. And so mu of x is going to be the expected value or the mean of the sum. And by what we've done before, by linearity, the expected value of a sum is the sum of the expected values. And now, if the random variables are independent, then the variance of the sum is the sum of the variances. If they're not independent, then this is not the case. In the special case when all the random variables are the same, then things reduce very nicely. And then you would get that the mean of the sum is just n times the mean of each individual one, and the variance of the sum is n times the variances. Now, whenever you have something that you always want to ask, is this reasonable? If we replace the xi's with, a1, x1, all that would happen is we would get a's into here. So we could do, the variance of a1, x1 plus dot 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 plus an xn with a very similar argument would become a1 squared variance of x plus dot 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 plus an variance of xn. So the very straightforward calculation shows you can do that. If you want, the simple proof is just let xk tilde be ak xk, and just apply the theorem to ak. Yes. Oh, sorry, the last one should be an squared. Everything else was squared. And so you always want to see what's the fastest way you can prove something. You never want to do the algebra multiple times. And so if I know this theorem holds, if I just apply to the xk tildes, where the xk tildes are just ak xk, then all that would happen is I would have the variance of 8, 1, x1, and I can just pull that up from before. So I actually can, it's sufficient to handle this simpler case and try to make the algebra a little bit cleaner than to have the a's propagating and floating around. Now, how many people might be interested in what their weight is? So when you look on the scale tells you so what? Hopefully what your weight is. What we can get into physics is it actually measuring your weight, is the weight, your mass is different than the foot, but we'll leave physics alone for now. So the scale gives you a number. Is the scale perfectly accurate? No. So what is the error in the scale? And what units do you typically use? Pounds, right? We're in America, we use pounds. What does the rest of the world use for the most part? Kilograms. But again, it's a simple conversion factor from one to the other. You never get pounds squared or kilograms squared as the uncertainty. Your weight is 145 plus or minus 16 square pounds. Hopefully the scale is not that inaccurate. So when we look at things like this, you always want to ask, what is the right thing to study? The variance is not a great quantity to study. What should we study? Study standard deviation. So the standard deviation, so we would get sigma x is equal to square root of n times sigma. And what this is telling us is that while the mean is growing, it's n times the mean of each individual one, the fluctuations are actually growing at the square root of n times the fluctuations of an individual one. And it's really important to get a sense of scale. So we can quickly look at this and we can see that the mean is going to go much, much faster. And the hope is that if we look at certain quantities, when we're trying to compute average quantities, if we're dividing things by n, maybe the variation is going to essentially go to 0, and we can get really accurate measurements when we look at, say, sample means. And that's going to be leading us towards the central limit there. All right, so now we need to prove something like this. And so the proof, depending on how much we want to do, is a bunch of algebra. So the really difficult one is the variance. So we want to calculate the variance of x1 plus xn. And this algebra is all in the book. So this is going to be the expected value of x1 plus xn minus the expected value of x1 through xn, which would just be mu x1 plus mu xn. So right now, I'm saying if the variables are independent, then we can simplify at the end of the day to this. So what I'm going to do is I'm going to keep the calculation as general as possible for as long as possible, and then swoop in and use independence. Right. So now when we look at what's going on, I claim this is the same as the expected value of, that we've got to square the whole thing. So I claim this is going to just be the same as x1 squared plus dot 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 plus xn squared, squaring all of those. Then I have all the cross terms plus x cross terms plus x's times mu's plus, right? This should be enough to show you that this is going to be painful, right? So let's try to think, is there a better way to try to view what's going on and not try to do that? So you can see that if we would expand everything out, it's going to become a mess. So is there a good way to view what's going on? Now, one thing you could do is you could try to do this for small values of n and build some intuition. You know, take n equals 1, take n equals 2, take n equals 3. See if you can start to detect the pattern. We also have a hint in that we're trying to prove that it's the variance of x1 plus the variance of xn. So given that hint, what if we start writing it as the expected value of x1 minus mu x1 squared plus dot 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 plus xn minus mu xn squared. And now we'll have to do more stuff. But when you think about this, if I expand x1 minus mu x1 squared, I'm going to get an x1 squared. Okay, good. That x1 squared is going to be coming from when the x terms hits itself. I'm going to get a mu x1 squared. Good, that comes when the mu's hit each other. Which one here? The whole thing is squared. It's this, the sum of the x's minus the sum of the mu's. I'll make this parentheses red to make it clear that they're all contained. And so when I'm squaring it, when the x's hit themselves, I'm going to get an x1 squared, an x2 squared, an x3 squared. Okay, this stuff is going to give me the individual x's squared. When the mu's hit each other, I'm going to get the individual mu squares. I'm also going to get your x1 hitting mu x1. And that's going to give me a negative 2 x1 mu 1. And so that gives me the cross term here. Okay. But I'm missing a bunch of terms. What terms am I missing? Yes. Yeah, so I've also got terms like, you know, x1, x2, x1, x3, x1, x4. I've got mu1, mu2, mu1, mu3, mu1, mu4. Maybe I can somehow combine those terms together. And so I've got to have, let's write it maybe as, you know, the sum of, you know, I less than j, xi, xj, and each of those I'm going to have twice. And then I have the mu's, right? And so when I have the mu's, those will also be plus, I think, a 2 sum I less than j mu xi mu xj. What else am I missing? Yes. Right, and now I also have an xj hitting a mu I, right? And then a mu j, so, right? And I'll have a minus 2. And now I got to be very careful as to how I do my sum here. So I can have all the x's hitting the mu's, but you don't hit your own one, right? So it's going to be like an xi mu xj. how do I want to do this? Maybe I could just sum over all I not equal to j. And in fact, if I do that, a better way of doing what I have over here is let's get rid of the factor of 2. Erase this one. And so now, what if we do I not equal to j, I not equal to j? Is that essentially the same as doing the sum twice? So before I had x1, x3, and I counted it twice. Now I have x1, x3, and x3, x1. So again, I would never make you do anything like this on an exam because I would then have to read it. But I want you to just see how to do it. And I think it's more valuable to just talk about the process than to really just write everything and just go through. How would you try to find a way to do this? And now can you begin to see the similarities in what we have? So we're going to use the linearity of expectation again. And this will be, the expected value of x1 minus mu x1 squared plus dot 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 plus the expected value of xn minus mu xn squared. So that part is exactly what we would expect. That part is coming from the beginning. And now we have the red part. And so for the red part, we're going to have a sum over I not equal to j. And it's going to be the expected value of, we'll have xi xj minus 2. Well, I'm going to write this as xi mu xj plus xj mu xi plus mu xi mu xj. So hopefully it'll be clear why I want to write the two that way. I'll write it once as xi mu xj and once as xj mu xi. Doesn't this look like a nice thing over here? And so if we now just continue with what we have, we just have the variance of x1 plus the variance of xn plus, and now we'll have a sum over I not equal to j, and then it's just the expected value of xi minus mu xi times xj minus mu xj. So what I'm trying to do is I'm trying to show you a logical thought process as to how we would get to this place. Yes, did I make an algebra mistake? Yes. It's more than just equivalent. It is the covariance. And so we will just say right now, this is the covariance. It is 0 if independent. So if all the x's are independent, then the expected value of the product is the product of the expected values, and then that's 0. And then you're left with just the variances. So the purpose of this calculation is to set ourselves up a little bit for what comes next. And again, what I really care about this is the thought process, is we know that we should be getting something like the variance of a sum should be related to the sum of the variances. So I want to have terms like an x1 minus mu x1 squared. So let me just take all the crap that happens from the definition, and I take from the crap the stuff that I know I want to get at the end, and I'm left with some other stuff. And then the question just becomes, what is the best way to write that other stuff that I have? And I initially thought, well, why don't I write it as twice the sum with I strictly less than j? And I thought, oh, well, if I do it like that, then that makes it a little bit more complicated over here. Let me just do a sum over I not equal to j. And so now we have the variance of a sum is the sum of the variances if independent. Yes?
It is void because I less than j is not.
Correct. And so over here, if I have I not equal to j, this double counts the pair 1, 3 and the pair 3, 1. And so a lot of times in the covariance, you'll have a 2 and you'll have a sum of I strictly less than j. And when you do a strictly less than, you will absolutely make sure you don't take I equals j. Okay. And so surprisingly, what the next slide is, here is the covariance. And so I'll maybe expand this out, make this a little bit easier to read. And so, from the calculation we were just doing a moment ago, we are defining it here as I strictly less than j. We could, of course, replace this with the sum I not equal to j, and that incorporates the 2, and then just the covariance of xi, xj. And we often write for this sigma xy, xi, xj. Okay. We're not going to do too much with covariances in this class. It's much nicer when everything is independent. So we will often assume things are independent. Okay. So we've discussed the method of cumulative distribution function before. You need some papers or something to dry that? So we talked about variances and covariances in the past. Not too much. We have talked about the method of distribution functions. And so I'm not going to go through a calculation again right now. If there's time at the end of the class, I'll look at it a little bit in greater detail. But I wanted to just state it here for the record. Sometimes it's nice to just have the slides having a bunch of things that are just all useful and all in one place. Okay. So we've talked about convolution as well. And so again, just stating this so it's all in the record, the convolution of two functions f and g. So we write, I guess, fx and fy, we write as f star the other, and it's just the integral of fxt fy of z minus 2. And if you think about this, if I want the sum to be equal to, say, z, if the first variable equals t, the second variable has to equal z minus t. Okay, you could, of course, write things with a discrete sum rather than an integral. I prefer to write things with integrals, and so for the most part, I will write it that way. But of course, you can do the calculation using summation as well. And then the big theorem is that if you have independent random variables, then the density of the sum is the convolution of the densities. We will be using this time and time again when we go into the central limit theorem and trying to attack that. So we just reviewed stuff that we've already done, so no new material was covered for you. Okay. So the central limit theorem, and this is the big thing we are building up to this semester, is the normal distribution with mean mu and variance sigma squared is e to the negative x minus mu squared over 2 sigma squared, and the normalization constant is 1 over square root of 2 pi sigma squared. So this is a plot of the Gaussian. And the big theorem is that if you have a sum of independent, identically distributed random variables with mean mu and standard deviation and variance sigma squared, and then we need some technical assumptions, finite moments is enough, then the normalized sum, so what's normalized sum? I sum the random variables, I subtract off n times the mean, because that's what I would expect to be at, and I divide by sigma square root of n, because that's the standard deviation. So what I'm really doing is I'm standardizing my random variable, so this quantity, this Sn, has mean 0 and variance 1. So this is mean 0, variance 1. Is it variance 1 or is it standard deviation 1? You sure it's standard deviation 1 and not variance 1? Yeah, they're the same thing, right? This is one of the nice things about having things normalized so that the standard deviation is 1. It's the same as the variance, except for the units. The units are different. And so what we're doing is we're standardizing or normalizing our random variable so that this sum has mean 0 and variance 1. And what this is that as n gets larger and larger and larger, it converges to a standard normal. So I can't remember if I've shown you these slides before. So just in case I haven't, I'll just do them right now. Let's take a uniform distribution of -1/2. And let's standardize it so it has mean 0, variance 1, and compare that to the normal distribution. So do you think a standard normal is pretty close to the Gaussian? No, it's not horrible, but it's not great. What about a sum of 2 uniform distributions, like rolling 2 die and adjusting it? It's not horrible, right? Already with just 2 die, it's not horrible. Yes.
The area under the curve, is it slightly different?
The area under the curve should be adjusted, I think, to be 1, because it should be a probability distribution. And you can see it's got a little bit more under the blue over here, but a little bit less over here. So it should hopefully be balancing out. But that's a very good check to be doing. Here's the sum of 4 uniforms. How does that look? Were you surprised that I went from doing 2 to doing 4? What is missing? 3. The reason you do 4 is you can do 4 as you can do x1 plus x2, x3 plus x4. And each one of those is a triangle. And now I'm convolving triangle with triangle. So there's an advantage to working with powers of 2. So the next one to look at would be 8. And so if I look at 8, you can see that is extremely close to a Gaussian. If anybody is looking for pain, I strongly urge you to explicitly write down the closed form expressions for the densities. This is the density for the sum of 4, uniform random variables, normalized. Mathematica was not happy when I asked it to do 8. And I might be able to play some games with it and basically override Mathematica and say, no, I really want you to do this calculation. You can see that this is a nightmare. You do not want to work with this. This is the power of the central limit theorem. Look at this. Among friends, is this close enough, to a Gaussian to just say it's a Gaussian? The error is so small that for a lot of the things we're doing, it's close enough. Especially if you're estimating parameters anyway, and you're just approximating the real world. This is the power of the central limit theorem. Rather than having to try to work with the closed form densities like this, we are able to approximate them. And that's the power. Okay. So it's time to start learning more distributions. And whenever I give you a distribution, after you know its name, what's the first question you should ask the distribution? Well, I mean, we're assuming we're among friends that we're not going to associate with something that's not a probability distribution. What's the mean? What's the variance? And if you really want to get to know the distribution well, you could ask what its third or fourth moment. It's very rare that we talk about the kurtosis or skewness in an introductory course, but these will give you some information, a little bit about how it's shaped and whatnot. For the most part, mean and variance are fine. So the Bernoulli distribution is probably the simplest one I can give you. So X has a Bernoulli distribution with parameter P, which is in 0, 1, means the following. The probability X equals 1 is P. The probability X equals 0 is 1 minus P. We can view this as the flipping of a fair coin. If P equals 1/2. If P doesn't equal 1/2, it's flipping a biased coin. We are counting a head as a 1 and a tail as a 0. Is there any other choice you might want rather than 1 and 0? There's one other choice that you could say is a good choice. So rather than giving a head of 1 and a tail 0, you can give a head 1 and a tail -1. And then if you do that, you would expect the sum to be 0. So if you flip it many, many times, it's now going to be centered about 0. And then the sum would be like the number of excess heads to tails or something like that. All right, so this is probably the easiest random variable we can study. Let's calculate the expected value of X. So this is the sum you have the probability x equals n times n, and we go over all n. Right, that's the definition of the expected value. We weight each outcome by the probability it happens. Well, there's only two outcomes. It's 0 with probability 1 minus p. It's 1 with probability p. So its expected value is just p. What if we wanted to calculate the expected value of x squared? That would be the sum over n squared times the probability x equals n. Well, that's just 0 squared times 1 minus p plus 1 squared times p equals p. So in fact, all the moments are going to be very easy to calculate. The third moment, the fourth moment, the fifth moment. Now let's calculate the variance. What formula do you want to use to calculate the variance? Do you want to calculate the expected value of x minus mu squared? No, I'm giving you the expected value of x squared and the expected value of x. It's much better to use, this is just the expected value of x squared minus the square of the expected value of x. So that's going to be p minus p squared, or p times. And note that this is a number in 0, 1. So, we are getting a non-negative variance. Where is the variance largest? What value of p makes the variance largest? 0.5. So why 0.5? So if I give you fp is p1 minus p, how would we take the derivative?
How would I go back?
Yeah.
I would rather view it as p minus p squared.
Excellent. Excellent. So we view this as p times, I'm sorry, as p minus p squared. So you would Thoreau it. So Henry David Thoreau is my favorite of the New England Transcendentalist writers. His great advice from Walden Pond, cultural extra credit. 2 words, but it's the same word twice. Simplify, simplify. This was from his year living on Walden Pond. Before you start doing a painful algebraic calculation, stop and think, is there a better way to do this? And the answer is often yes. Simplify, simplify. So f prime of p is going to just be 1 minus 2p. So f prime of p equals 0 implies p equals 1/2. F double prime of p is -2. So it is a max. So this makes sense that the variance is largest when p equals 1/2, because then half the time you expect heads, half the time you expect tails. If p gets closer and closer to 0 or 1, you basically have very little variance. You basically just keep, you know what you're going to be getting. All right, so this is a really good calculation. Any questions on the Bernoulli distribution? All right, so the last thing I want to do today is I want to talk about the binomial distribution. So again, n is going to be a positive integer, p is a parameter between 0 and 1, and in the binomial parameters n and p is the following. So the probability that x equals k is n choose k, p to the k, 1 minus p to the n minus k, for k between 0 and 0 otherwise. And we write this as binomial np, and then the big result is the mean is np, and the variance is np 1 minus p. There's a couple of ways to do this. One is we could view x as x1 plus xn for each xi is a Bernoulli with parameter p and an independent. So essentially what we're doing is we're flipping a coin with probability p n times. And this records how many times we get ahead. Well, how many times would there be? There's n tosses. I need exactly k of them to be heads. So there's n choose k ways of choosing which k slots are heads. And then to get ahead, it's probability p. So I have a p to the k. All the other ones have to be a tail. That's 1 minus p to the n minus k. The advantage of looking at it like this is we can write the expected value of x as the expected value of x1 plus dot 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 plus the expected value of xn, which is just going to be n times p. Which makes sense. If each p coin basically is on average p, then how many heads do you have? N times p. And because they're independent, the variance of x is just going to be the variance of each one. And so it's going to be n p 1 minus p. So notice how easy it is to do this when we view things as linearity of expectation. Yes. Oh yeah, I mean, if I ask you, what is the probability you get 17 heads when you toss the coin 4 times? It should tell you, shut up, don't ask me that question. I don't want to consider any values of k other than. Now, exactly. And in fact, if I give you 5 choose 3, this is 5 factorial over 3 factorial, 2 factorial, which is 10. What is 3 choose 5? How many ways are there to choose 5 people when order doesn't matter from 3? 0. This is the same as 3 factorial over 5 factorial negative 2 factorial. So negative 2 factorial is what? Not 0. Infinity. It has to be some type of infinity. And we'll see this with the gamma function. Later in the semester. So there is a way to generalize the symbol. One of my favorite results is we will see gamma of n plus 1 is n factorial if n is a non-negative integer. And it will lead to a generalization of the factorial function where negative 1/2 factorial, the number of ways to arrange negative 1/2 of a person when order doesn't matter, is the square root of pi. Does anybody remember where we've seen the square root of pi today? Was on one of the slides. Yeah, it's the normalization factor of the standard normal. It actually comes down to the gamma function. It actually comes down to negative 1/2 factorial. And so we will see that later. So when you look at stuff like this, it's a really good question as to where is a formula valid? And here it's extremely important that we only use this for k's that are integers from 0 to n. Anything else, it should assign the value of 0. And then what I'll end with today, rather than doing the calculation, is the, let's say x is binomial NP. The expected value of x is going to be the sum, k goes from 0 to n of k times n choose k, p to the k, 1 minus p to the n minus k. The expected value of x squared is the sum, k goes from 0 to n of k squared, n choose k, p to the k, 1 minus p to the n minus k. We know x plus y to the n is the sum, k goes from 0 to n of n choose k, x to the k, y to the n minus k. Does this help? Can we somehow use this to attack these results? And the answer is yes. It's a method called differentiating identities. And we'll talk about that in next class. It's one of my favorite methods in all of mathematics. This is a good place to stop.